Hi, and welcome to this next video in the integration section from the Year 2 part of the Math A-Level course. And in previous videos we dealt with one of the big techniques that you learn in Year 2, which was integration by parts. Here comes the other big one, which is integration by substitution. And in both of these cases there are ways of being able to get around essentially integrating products. So what we're going to do is integrate by substitution, and then the second part of the video we'll have a look at how we deal with limits and issues surrounding those. So here we go, integration by substitution. So often you're going to get products to integrate that don't work by parts because of the nature of them. You need, when you're integrating by parts, one of the products to break down to become essentially a constant, or apply one of the sneaky tricks we've talked about previously. In both of these cases here, that's just not going to work, so we're going to need something completely different. So here we go. What we're going to do is we're going to do a substitution, and an obvious one to pick in this particular case is to let u equal x squared plus 1. So now what we're going to do is, at the moment, our variable in our integral that we're looking at is everything is in terms of x. What we're going to do is change everything to be in terms of our new variable, which is u. So what we're going to have to do is, we can clearly replace this bit, we're going to have to replace the x somehow, and also this dx part here that up to now possibly you might just regard as being a notation, meaning do it with respect to x. We've got to replace that as well, so we're changing it to du, i.e. do it with respect to u. So what we're going to do is basically replace x throughout the entire integral. So here we go. Let's start off by just using our substitution. So I've replaced the x squared plus 1 with a u, but you can see we've still got lots of x's. We've got this thing here, and we've got this dx we've got to deal with, so there's clearly a lot more that we've got to do. Let's have a go now at thinking about how we can replace that dx, and the way I'm going to do that is by doing some differentiating over here. So du dx becomes 2x, and all of a sudden this dx thing has appeared here. That's the bit I want to be able to replace. So what I'm going to do is make that the subject, and I can make that the subject by essentially moving the dx over that side, bring the 2x back that way, and there we go, we've got dx equals du over 2x. So let's now substitute that in. So we've got that. And you might be thinking, well, hang on, you still need to replace the x, but if you have a look at what's just happened, you've got an x up here that will cancel out against that x down there, so that essentially solves that problem. So I would always advise doing this step first and seeing if you can get some cancelling to go on, which will make your life a bit easier. In this case it has. We've got a 2 on the bottom, so I'm just going to refer that as a half and take that outside my integral. So now that whole integral there, because that substitution has just become nice and simple, and we've now got something we can integrate with respect to u. So let's do our integrating. So let's integrate u to the power half, which becomes u to the power 3 over 2 times by 2 over 3. And then the last thing we need to do is, because our original integral was up here in terms of x, we just got to redo our substitution. We can do a bit of tidying up with these fractions. So we end up, there you go, there's the fractions gone, and we end up with 1/3 x squared plus 1 all to the power 3 over 2. And finally, because it's an indefinite integral, never forget the plus c. And jobs are good. And then we go to part b. So we've got 2 sine 2x over 1 plus cos x. And so again, let's apply exactly the same principles. Let's start off with a substitution. We're going to pick 1 plus cos x as our substitution for u. So that differentiate it. I would always do that bit first. So du dx is minus sine x. And so that gives us dx equals du over minus sine x. Once that bit's all done, now let's start plugging that back in and seeing what impact that has. So we've got 2 sine 2x, I've got the u on the bottom, du over minus sine x, there's my replacement for dx. And you can see we need to get rid of the x's, so we haven't completely done that yet, so let's just see what else we can do. The problem that we've got here is this thing here is sine 2x, this one's in terms of sine x, they're not just going to cancel out. So let's just take our sine 2x, and we should know that sine 2x is 2 sine x cos x. So there you go, let's do that. And you'll notice I've just popped the 2, this 2 here, I'll just pop that outside. Now we can do some cancelling. So let's cancel out the signs. Again, another little bit of tidying up. This 2 here has come out the front to make that 4. I've taken the minus sign, that's come out the front as well. And so the last thing we've got now is that cos x, still in terms of x, we need it in terms of u. And to do that, we're going to go back here, because we say u equals 1 plus cos x. So let's just switch that around a bit and say, well, that gives us cos x equals u minus 1. So now let's put that in, because that cos x is u minus 1. Let's put that in there, and there we go. Now, what we're left with there is a fraction, and fractions are not the easiest thing in the world to integrate, but this one particularly is a lot more simple. Because we've just got a single term on the bottom, we can separate this out. So we've got u over u, which is 1, minus 1 over u is minus 1 over u. So there you go, I can write that as two separate bits, and now we've got that looking like something that we can easily integrate. So let's crack on and do the integrating. So to do that, we end up with that. So we're doing it with respect to u, so integrate 1, I get u, integrate 1 over u, I get ln u, and so there I've done the multiplying out by 4, and then the last thing we need to do is to resubstitute, so let's put our u equals 1 plus cos x back in, and there we go. Let's just check. So I've just done a little bit of tidying up, so the u there, that's the 1 plus cos x, and this term here, so that's minus 4 times by 1 plus cos x, and that gives us those two bits down there. So I'll just take a moment to make sure you're happy. That bit down there is minus 4 times by 1 plus cos x, and my plus c, and there it all is, tickety-boo. And so, cracking swiftly on, here we go. We've got another integral. So this, I've seen quite a few of these ones appear in exams, because what we've got here is a not a particularly obvious substitution. The substitution that's been suggested is we're going to let x equals 4 sine squared theta, which seems like a slightly bizarre one. If it is one like that, one that's not immediately obvious, then in the question in the exam it will tell you exactly what the substitution is that they want you to use. If it doesn't tell you what the substitution will be, then it should be fairly straightforward and obvious. So what we've got to do, we've got to find the area under the curve being square root of x over 4 minus x. We've told the substitution, we've got limits, and says find the exact value of r. Okay, on we go. So that's the integration that we need to do. That is the substitution that we're being told to use. So my first job will be to do some differentiating. And if you remember differentiating sine squared, that's going to be a chain rule by inspection job. So we've got to bring the power to the front, then differentiate sine to get cos, and then take one off the power. You do all of that, we're going to get dx to theta equals 8 cos theta sine theta. Again, this is 8 because we've got the powers come to the front and times by the 4. And just a bit of rearranging, because we want to replace the dx. So we've got dx equals 8 cos theta sine theta. Right. Let's chuck that in. So that's what we've got. We've replaced the x with the 4 sine squared there. We've replaced that on the bottom there. And here, this section here, that is outside the square root. And that's my dx. Now, if we on the previous examples, this is the point where I'd be doing some simplifying and some integrating. But before we get anywhere near that, we've got one extra issue to deal with. And that is those things, my limits. Those limits are in terms of x, because we've got between x equals 3 and x equals 0, but we're now integrating with respect to theta. So those limits are in terms of x, but it's the wrong variable. So what we've got to do is we've got to turn those limits into limits that are expressed in terms of theta. So what are the equivalent theta values? Well, the link between x and theta goes back to our substitution here. X is 4 sine squared theta, so if x is 3, that was our upper limit, then we've got that. So our equivalent value for theta is just the solution to this equation, which is going to be root 3 over 2 equals sine theta, giving us theta is pi over 3. Similarly, if we've got x equals 0, we've got a value of theta equals 0. Now, in the exam, there will be independent marks for that, so you've got to clearly demonstrate, even if it's blatantly obvious that for a value of 0, for one, your new value is 0, demonstrate clearly that you get that, so the examiner knows that you're not just kind of chucking the 0 without understanding why. Right, having done all that, so let's just take out the 3 and the 0 and replace them with the new limits. So that's that bit sorted out. So now what we've got is the entire thing in terms of theta. So we had to replace all the x's in here, and we had to change these values into values for theta as well. Now, we've got a whole bunch of trig style tidying up to do, so let's just have a little look, and let's have a look at what's going on there. We've got 4 sine squared theta over 4 minus 4 sine squared theta. So, a bit of factorising. Hopefully we notice that 1 minus sine squared is cos squared. The 4's cancel out. And at this point, as soon as I see that, I'm seeing sine over cos. I'm desperately thinking tan, but in this particular case, I'm not going to replace that with tan because it's going to create extra problems, although my brain is screaming to me that that's what it wants to do. But I'm not going to, and you'll see why in a second. So let's just replace all of that with, so the 4 sine squared over 4 minus 4 sine squared, that's our sine squared over cos squared. And again, I'm desperate again, tan, it's going to be tan. No, it's not, because what's going to happen here is, let's do the square rooting of the squareds. So that leaves you with that. Now let's do some cancelling. And the whole thing ends up there. So we've got 8 times by the integral of between pi over 3 and 0 sine squared theta. And that's something we can integrate. If we'd have done the replacement with tan here, we'd have ended up with a tan theta times by cos theta sine theta, and it just wouldn't have been nice, or we'd have inevitably had to go back and do some reworking. So there we go. We've got it in terms of 8 times by the integral of sine squared theta between limits. And what you tend to find in exam questions is the first part of the question will be what we've got on the screen here, which is demonstrate that using substitution you get to this result. And then the second part of the question will be use the result to do the integrating. And so even if you don't manage the first part of the question, you've still got access to the second part. Right, we've done that bit of work. So there we go. We know what we're integrating. So we've got to integrate sine squared. How do you integrate sine squared? Well, we do it by using our cos 2 theta replacement. So let's replace the cos squared with a 1 minus sine squared in there. Do a bit of tidying up to make sine squared the subject. So we're there. So sine squared is half 1 minus cos 2 theta. Let's bash that back into here. There it goes. And we've got the 1 minus cos 2 theta. You'll notice I've got a half here, which I've times by the 8 to give us a 4 there. So now I can integrate that quite nicely. So there we go. Integrate 1, I get theta. Integrate cos 2 theta, I get half sine 2 theta. I'm thinking, have I got to do anything with sines? No, I haven't. Integrate cos, positive cos, I get positive sine. Integrate negative cos, I get negative sine. So that's not changing anything there. And then in we go with our substituting the limits and the intention to subtract. And there we go. There's the exact value of r. And there it is, all sorted. And so one more example that I'm going to do. Again, it's a substitution. We're given a substitution. This one's in terms of a ln function. So in terms of structure, what we've got to do is let's start off with u equals x squared plus 2 and work from there. So we've got du dx equals 2x. So that gives us dx equals du over 2x. So let's use all of that to, first of all, do some replacing of the x. So sub back in. There's my u going in there. There's my dx gone in there. I've still got some x's to deal with, so let's do some replacing there. So let's just do some cancelling. And so now I've got an x squared here. And again, I'm going to have to replace that, get it in terms of u. So I can do that from here. So we've got u equals x squared plus 2. So that gives me x squared equals u minus 2. So that's the substitution I can use there. So in it all goes. This half, that's the divide by 2 there. I've taken that out the front. And the next thing I've got to do is change my limits. So I've got my limits in terms of x here. So when x equals root 2, that gives me u equals root 2 squared plus 2. So that's u equals 4. And when x equals 0, that gives me u equals 2. So in go my new limits. And now that's what we've got to integrate. So we're going to do our integration by parts. So there's my formula. Remember, that formula is given to you in the formula booklet, so you need to be familiar with it. You don't have to remember it. You've always got access to it in the formula booklet. And my worry with this one is that we've done some swapping around to get a new expression in terms of u, but we're now going to use this one here, which got u's and v's. So what I'm going to do, I'm just going to rewrite the problem. I'm going to restate it, but I'm just going to go back to doing it in terms of x. Like that, so it's basically the exact same thing. It's just avoiding confusion when I start using this, because now I've got, okay, my substitution. Now here's the thing, we're going to let u equal ln x, because when I've got a ln in integration, it's always a good idea to use that as your value for u, because when you differentiate it, it breaks down to become a polynomial, which will cancel out against other stuff. So that gives me dv dx is x minus 2, which gives me v is integrate that, x squared over 2 minus 2x. Bang all those bits in. There they go. So I've got u times v. So there's my u ln x times by v, x squared minus 2x, minus the integral of, and we've got v du dx, v du dx. You can see now why it's a good idea to use ln x as u, because now we've got this x on the bottom that will cancel out against bits there. So let's have a look That's where we were before, so there goes the cancelling. So the x squared over x, that's become x over 2. The 2x has just become 2 there. So now we're just left with doing that integral there. So let's do that. X squared over 2 becomes, x over 2 becomes x squared over 4. Integrate 2, I get 2x. There's my limits from before, the new ones we used in terms 4 of 2. And the last thing I've now done, we've got minus this bracket here. So I've dealt with that. So the x squared over 4 is now negative here. And we can see we've got minus, minus, makes that a plus. So that's that all dealt with and nice and tidy. So now let's plug in our limits. So what we've got over here is 4 squared over 2, which is 8, minus 2 times 4, which is 8. So that's the 0 in there. So that gets rid of all of that bit there. And then we've got 4 and 8 coming in from here and here. Subtracting what happens when you put 2 in. And then it just becomes a numerical exercise. This first bracket here, I've got minus 4 plus 8 times by a half. That's 2. And over here, I've got minus 2 ln 2 times by a half. And I've got 3 times by a half. Making sure we're taking into account all the issues going on with sines. And then there it is. There's our exact value. Jobs are done.